I'm now recording, not quite yet, but as soon as you all go in with it, whatever, we're recording. Okay, now I want to start out with, I'm going to go to the book a little bit later. I want to start out with a different screen share here. If I can find it, yes. Okay. Now, this material is hard to read. So I suggest that you first concentrate not on the proofs so much. The proofs actually, I think, help you see why the statements of the theorems are what they are and how they work out. But we were trying to get first a view about vectors here and the properties of vectors. And people think certain things happen with vectors, and then we prove what we think. And so you change the intuition, hopefully, into mathematics so that you can prove things later with them. Anyway, you guys know some of this. This is in section 12.3. When we have the dot product of two vectors, and you know what that is, when it's 0, we say the vectors are orthogonal. You know that. Okay. So it's going to get worse than that theoretically in a second. But this is the perpendicular idea is because of 90 degrees, because you can equate the dot product to the cosine of an angle times the length of these vectors. And when the dot product is 0, the angle is 90 degrees. And so it turns out that orthogonality is a very important concept in what we're going to be doing. It involves planes and all kinds of other things. Now, but it's going to get more theoretical for a little while. One of the things, suppose we're in 10-dimensional space, okay? It turns out that there are things called subspaces. And the question is, what's a subspace? If we're in 3-dimensional space, and by the way, one of the things to do today is to define what dimension means. But if we're in the 3-dimensional space that we sort of live in, what is a 2-dimensional subspace? What's a 1-dimensional subspace? Do these things exist? So that's what we're going to talk about first. And so first, what is a subspace? We're going to say a subspace is a subset, okay? And if you just stay in that subset and add things together and multiply them by scalars, you still stay in that subset. So what we say is that the subset is closed under addition and scalar multiplication. So it itself is a vector space, all right? But it's a subset of the other vector space. Now, theorem 10 here tries to give you criteria for when you know you have one. So if we take a subset, non-empty, that has the property that I gave above, but if the sum of any two elements are in the set and the scalar product are there, then it is a subspace. It is a vector space in itself. Okay, that's the easy part. So let's talk a little bit down the line. The next thing is extremely important in terms of vectors, and that is what are linear combinations and what is the span of a set of vectors. Linear combinations mean take your vectors, in this case, if we have m vectors, like say 20 vectors, take a number for each vector. So take 20 numbers, scalar multiply the vectors by the numbers, and add up the result. That's called a linear combination. So when we talk about points in straight lines, for example, in the plane, and you know the equation of a straight line might be like 3x plus 4y equals 5. The left-hand side is a linear combination of the x and y. When you say 3 times x plus 4 times y, we're talking about linear combinations. So we've had linear combinations for years in your background. We just probably haven't called them that. And also when I say x and y a minute ago, I'm now talking about vectors, not just numbers. And so when we have a vector space and you combine vectors in this way, like if I add two vectors together, that's a linear combination, although we wouldn't probably think about that way at the moment. That's where the coefficients are both 1. And by taking various combinations, we get various other vectors. You know, from a physics standpoint, adding vectors gives you resultants. So what this is a resultant of applying M forces to something, okay? And you're adding them up, so you're trying to find the resultant. Now, if every scalar is 0, it's called a trivial linear combination. We only put that in because sometimes you have to have that in proofs. Now, what if we take all possible linear combinations of these vectors? What do we get? I don't know, but what we call it is the span. So if you take linear combinations of vectors, you get a span. Now, for example, suppose we take one vector in the plane or in 3 space and multiply it by numbers. What do we get? We get a whole bunch of things like 2 times the vector, minus 5 times the vector, and so on. When you put all those together, what you get is a straight line. Okay? So the span of a single vector will turn out to be a straight line. And it passes through the origin, because I could pick 0 to multiply the vector by. When I multiply a vector by 0, I get the 0 vector. So the span of a set of vectors always includes the 0 vector. Okay? So no matter what they are, if I add up linear combinations, the amount of stuff I get is called the span. All right. So, for example, I say here, and I'm going to go through this pretty line by line because I think you may have questions someplace, and I think we need to just talk about everything. When I take the 3 standard vectors, 1, 0, 0, 0, 1, 0, and 0, 0, 1, what do you get when you add those up? What's the span? And the answer is the whole 3-dimensional space. You can get every vector in 3 dimensions by taking a number times 1, 0, 0, a second number times 0, 1, 1, 0, 0, 1, 0, and a third one times 0, 0, 1. So one example, if we take these particular 3 vectors, we get all of the what we call 3-dimensional space right now. And by the way, we're just using the word dimension intuitively. We're just calling it that to try to identify it, not to use it mathematically yet. Okay, very important concept here is when vectors are linearly independent. Now, a set of vectors is either linearly independent or linearly dependent. Now that in itself, that's true about anything. You're either big or you're not big. Okay, that's fine. So that doesn't explain what it is. That if I know what one of the 2 concepts is, then I know the other concept. But we're going to spend part of the day today trying to understand the difference between independence and dependence. Okay. So the statement is the linear independence of a bunch of vectors, 20 vectors, as we said a while ago, is any linear combination that adds up to 0 vector must be trivial. Now, what does that mean? That if you assume you have a set of vectors and combination of vectors adds to the 0 vector, then every coefficient must be 0. Now, as an example, suppose we take the I, J, and K, the 100, 010, and 001. Suppose I multiply I by A, that'll give me A00, and multiply J by B and K by C, then I will get the point ABC. If I assume that is equal to 0 vector, if I assume the vector ABC equals 0, 0, 0, then what about A, B, and C? They have to all be 0. If ABC is 0, 0, 0, then A is 0, B is 0, and C is 0. And that means I, J, and K are linearly independent. Okay? It's not always that easy, but that's what you do. If it's not the case that they're independent, then they're dependent. So what does that mean? Well, if you take the negation of the sentence describing independence and you say it's not the case, then what you're saying is that there are scalars that aren't all 0 that you can make a combination up that adds up to 0. So either if you have a combination that adds up to 0, all the scalar numbers are 0, or there is some non-zero scalar that you can make up a linear combination that adds up to 0, and at least one of the things is not 0. So we will be using that, okay? Vectors are called independent if they're not dependent, and so on. We already said that. Okay. If the vectors are independent and span the whole space, then we say the vectors are a basis. So what we've just verified is that I, J, and K are a basis for the space we call 3 space, or the space we just call space, because of the space we live in. Okay, now there's a bunch of theorems about these things to try to give us some understanding about independence and dependence. And these things are going to underlie what we do all semester. And so you're going to find out that these are very valuable as we go through the semester. Right now, some of it may not make much sense, but once you see some of the uses of it, it'll be like, oh, that's what the thing meant back there in those pages that he made me read, or he asked me to read it. Okay. First, theorem 11, and I'm just, if I have a set of vectors, okay, I'm sorry, if I have a set that is spanned by M vectors, then that is a subspace, okay? So when you span with vectors, you get a subspace. Okay, let's talk about this. 0 is a subspace, just the set with 0 in it. One object is a subspace. Now, if the object was something besides 0, it's not a subspace. But 0 is, okay? Why is 0 a subspace? You take anything from there and add them together, you get 0. So it's closed under addition. You multiply by any scalar times 0, you get 0. It's closed under multiplication, scalar multiplication. So it's a subspace, okay? It's also linearly dependent. One vector is dependent because I can multiply by a non-zero scalar to get the result 0. When you multiply 1 times 0, you get 0. So when you take the point 0, it's a linearly independent set by itself. The span of the set is itself, okay? It has no non-empty linear independent subset, so it has no basis. We declare the single point 0 to be a subspace of dimension 0. We're trying to define dimension today, among other things. So if I just take the point in the very center of things and just it, that's called a subspace of dimension 0. Now, if I have, again, 20 vectors, we said M is 20 just to illustrate. If 0 is one of them, so in your list, if one of them is 0, then those vectors are automatically dependent. And I try to explain it here. You can try to read it through. I want you to, I'm not going to try to explain every single thing today because it'd take more time than we have, but you can read this, see why I said it, mark, if you don't understand it, go over here and mark it in pencil. And on Friday or in some other time, call me, email me, say, I don't understand why this paragraph. And then you and I can go through this paragraph until you understand it, okay? So I'm not going to explain every paragraph just because of time, but please go through it, all right? If you include zeros in one of the lists, the vectors are automatically dependent. Okay, what's the next thing say? If I take a non-zero vector, then by itself, it is independent, okay? So if it's non-zero. Anyway, now we're taking everything in n-dimensional, what we call n-dimensional space. That's just n tuples. So if this is 20-dimensional space, everything will have 20 components. And I say here, we have directions, you know that. Every other vector in S has this direction or other. Suppose, I'm sorry, I'm trying to see what, okay. If I have a straight line, so if I take one vector, okay, and make up the span of it, That's, I told you a while ago, if you think about it, that's 3 times a vector, 10 times a vector, and so on. That gives you everything on a line, okay? And it turns out that this is something that turns out to be what we call dimension 1. The span of a non-zero vector gives us a subspace, and it will be what we call dimension 1. So straight lines through the origin are vector subspaces. I'm not talking about straight lines anyplace else, but if they pass through the origin, they are subspaces. Okay, so let's go through some more of these things here. Just kind of talk about them and see if you can, I want to read through it and see if you kind of understand as I read it, or if you have to read it yourself, whatever. It's hard to know when you understand stuff. If I have, again, 20 vectors and take the span of the vectors, if the vectors are independent, then anything in the span is uniquely represented by the coefficients. And so these become like coordinates that you can use to identify the vectors. So if I have vectors in a span, and any vector that's a linear combination of them, the coefficients make a set of coordinates. Like when we say E1 or I, we say 100. That's a set of coordinates that identifies the vector. So theorem 12 talks about that. What's theorem 13? If I have 20 vectors, they're dependent, then any sequence containing these vectors is also dependent. So if you have 20 vectors and take 10 of them, if the 20 vectors are dependent, then the 10 vectors are dependent. Okay? What's the contrapositive of that? Contrapositive means turn the if-then sentence around and put knots on it. It's equivalent. That would say if the 10 vectors are independent, then the 20 vectors. Anyway, we'll talk more about that. 14. Suppose I take 20 vectors, take the span. If something between 2 and 20 is such that it is in the span of the preceding ones, so suppose the 9th one is in the span of the first 8, okay, then the span of the everything except the 9th one is the same as the span of the 20. So if you have something which is in the span of the preceding ones, you can remove it and you don't lose anything. You can describe the space, the span, using one less vector. Okay? So for example, if we can describe three-dimensional space with 3 vectors and you have 4, that's okay, but you can get rid of one. Some of these things will make more sense as we go through, okay? Now, this next theorem, and unfortunately there's not too many more theorems, but if I take 20 vectors that are all non-zero, now that, remember if you have 0 in there, they're dependent. If I take 20 non-zero ones, and there's something between, like we said, number 9, suppose number 9 is in the span of the preceding ones, okay? That can only happen if the 20 of them are dependent. So you can look into that. Okay, 2 more and then we're done with the theorems, I think. This one says, if I have 20 non-zero vectors, take the span and suppose the span is everything, the whole space, then some sequence of the 20 is a basis. Okay, when we have a basis, we are able to identify all the points. So we're always looking for a basis when we do this stuff. And so this number 17, I said last 2, there's another one. If I take M non-zero vectors, 20, and they span the space, suppose something in between one and like number 9 again, is such that the first 9 are independent, then there'll be a basis among the first 9. That's what theorem 17 says. Theorem 18 says, if I have a basis of 20 elements for the vector space V, any other basis has exactly 20 elements. So if you can find a basis, any other basis will have the same number of elements. Now, earlier we said I, J, and K is a basis for E3. Therefore, any basis for E3 has 3 elements. That is what we call the dimension. So the dimension of the space is the number of elements in the basis. So if you find the basis and you can count it, the number of elements is the dimension. Why do we call the plane two-dimensional? Because the vector 1, and the vector 1 are independent and span the whole plane. There are 2 of them. That's why we call the plane two-dimensional. Okay? So I say that here. And we wanted to do some examples or not. So what's left here is talking about what's going on in terms of what we just said for the last few pages there. And one is if I have n vectors in En, the Ek, the 100 and the 000 and all that 1 and all those are always a basis. So in E3, you have a basis ijk. In E2, you have a basis ij. Of course, these are different in the 2 worlds. Okay. And this is why En is called n-dimensional. Okay. Number 2, suppose I have a bunch of orthogonal vectors. Now, orthogonal, that doesn't mean the vector itself, it means pairwise. Suppose 2 vectors are orthogonal. That means the dot product is 0. So I got 20 vectors and their dot products are all 0. Then they are automatically, not well, you have to prove it, but this is what this says, they are independent. So orthogonal vectors form an independent set. That turns out to be important sometimes. If you prove something is orthogonal, they're automatically independent. Now, let's go back and look at a straight line. Suppose I have a straight line y equals mx. You know about that from years ago. Okay. Now, you also know there's a one-to-one correspondence between non-vertical lines and slopes. Every non-vertical line has a slope. Every slope is a non-vertical line. You guys know that. If the direction is given by, take the vector, that's what a direction is. Remember, this direction is length 1. Then what's the slope of the line? Turns out to be b over a. Now, you might not have thought much about that, but you can now. If I have a direction, AB, the slope of the line is b over a. The equation of the line becomes y equals b over ax, and you can write that as this, or you can write that with dot products. So the equation of a line in the plane, we know that this formula, you know generally this kind of formula, and so this line, by the way, is going through the origin. Not all lines go through the origin, but the vector subspaces do. So b minus a is a vector that's orthogonal to every point on the line. Such a vector is called a normal vector, and so on. Now, you haven't needed to have normal vectors when we talked about equations of lines in algebra, but once we get into more than 2 dimensions, we do, because we no longer have the thing called a slope. When I have a 3-dimensional line, a line in 3 dimensions, it doesn't have a slope. Okay? You can envision the thing going along, but it doesn't have a slope. So, now, if I take 2 non-zero vectors, make 2 of them, if they're independent, there are numbers, these are scalars, not both 0, so that when I can add them up and get 0, that means one is going to be equal to minus the concept of the other. So basically, when I have independent vectors, they are scalar multiples of each other if I have 2 of them. That's what this number 4 says. Okay. If they're independent, they span a two-dimensional subspace. So lines in the plane, two-dimensional subspace is a plane. So suppose I'm in 20 dimensions again. If I take two independent vectors, they will span a plane. So even if I'm in 20 dimensions and I can't see that, if you give me two vectors, the plane looks like a plane that you're used to in 3 dimensions. So you can visualize stuff in 20 if it's two-dimensional because it looks the same way. Now you can't visualize how it looks with the other 18, but you can see the flat thing in the 20 space. And so we can live with it. I mean, we can still use our visual ideas of things in multi-dimensions that are higher than 3. And we can't see the whole thing, but we can see subspaces, namely up to 3-dimensional subspaces. So in 4 dimensions, you can see 3-dimensional subspaces. I don't mean see in the sense of, since we can't see 4, you can't see 3 in 4, but you can think of 3 being in 4 without visualizing 4. Now, I don't know how that's going to sound on the recording, but I'm hoping that makes sense. Okay, and the last part here in these notes has to do with equations of planes. And so what we do is we generalize the idea of a line, as I just said. We had equations of lines without normal vectors, but with the equation of every line, there is a normal vector. And that's involving the coefficients that make up the linear combination. Well, in 3 dimensions, it's a similar idea. And it turns out that if you have a vector that is orthogonal to a bunch of other vectors, that vector, which we call n, is called a normal vector. And if you dot it with all of those, you will get a plane. So a plane through the origin is a linear combination of a, b, and c, and x, y, and z, where these are, when you add these up, you get 0. This is a plane through the origin. Every plane through the origin looks like this. So if you want a plane through the origin, you just make up a is 5, b is 3, and c is 7. Make that literal thing up, that equation, that will give you a plane. On the other hand, if you have 3x plus 7y plus 4z equals 0, then 3, whatever I said, 7, 4, whatever I said, is a normal vector. It sticks out of the plane in terms of the way we visualize it. So what this material here in these pages here is trying to talk about what is in section 5, okay, which we'll be talking about shortly. Anyway, and one of the things about these things is if I look at an equation which turns out to be the equation of a plane, if it's not vertical, then there's a z as well. And if you look at this equation, the things you don't know are this number AC and this number BC. So as long as you have a z involved, as long as z is a function of 2 variables, like z is ax plus by, then you get a plane. You see, a little earlier we had this. Now, if c is not 0, then I can divide by it, and I can set c equal, and that's where you get this right here. So any non-vertical plane can be written this way. The coefficient of z is 1 in this case. So I just need to know what these two things are, and I would identify my plane. So if I know what A and B are, I can identify my plane. Now, if this equals 0, then AB would be normal, would be perpendicular. And what we're going to get into is what are parallel planes. So this plane with A and B here turns out to be parallel to the plane through the origin with AB as a normal vector. And when I say that, that's incorrect. Sorry. AB minus 1, the third component will be minus 1. So if I have this equation and I want to say what plane is it, I could rewrite this as AX plus BY minus Z equals 0. And then I could extract the coefficients A, B, and minus 1. And that is a normal vector to the plane. That sticks out of the plane if you want to think of it that way. It is perpendicular to everything in the plane. We're going to be dealing more with this, a lot more with this, but I thought you ought to see or have me go through this a little bit. Okay, so that's all I want to say right now about that. You guys need to read this over and over. It will all get much, I mean, taking time to do this now is when we get later in the semester, this stuff will help you understand everything else we do. So, but if it's hard to read, okay, it's hard to read. If I'm going a little deeper than the book does, okay, so what? We need to know how much I'm going to require of you later, not how much you should study now. Now, we don't seem to have one extra person, which I'm sorry about. Whoever that is, don't know who it is because I have no idea who's here and who isn't. But I'm going to take a snapshot now and then change direction a little bit. So where is the participants? Okay, I now have a list of participants on my screen. I'm going to take a snapshot of you. I apologize for the time, but it's the easiest way to do this. While I'm doing this, you might consider the following thing. Students in the other class, one student in the other class, said, would it be possible to have class in person next week? So I want you to think about that till the end of the class today. Remember, when we do stuff, we have to do stuff together, do both classes. So if somebody wants to start having class in person. So think about that a little bit, and we'll talk about that in a little while. Okay, I guess you can see me at the moment. I need to go to a different screen. Where is it? There it is. Okay. Now, I left the book open here to this page because this is about quadrics. We're not ready to do this yet, but some of you may be bored with all these notes you don't understand. You might want to go look at some nice pictures. And so in section 6, the book talks about this. We will be talking about this, but not right now. I want to do something else. And that is in section 4, we have the book talks about determinants. Now, in Calc 2, for those of you with me in Calc 2, we actually went in and defined determinants, if I remember right. Right now, I'm not going to go to all that trouble. I just want to talk about some arrays. And if you're not familiar with this, it's okay. This will be a light touch to begin with. When I have rows and columns like a spreadsheet, okay, we think of, in this case, AB as being the first row of numbers in an array and CD as being the second set of numbers in the array. This is called a 2x2 matrix, M-A-T-R-I-X. And below here, I have a 3x3 matrix, 3 rows, 3 columns. It turns out that using matrices is a very helpful way to understand concepts in 3-dimensional or 5-dimensional or whatever calculus. What we're going to be doing, whenever we can use matrices, it's going to turn out to be helpful to us and an easy way to describe things. But there's a little bit of a learning curve with matrices. You have to figure out how to add them and how to multiply them and stuff, and we'll be talking about all that. But right now, I just wanted to mention determinants. I'm sure you had determinants in high school. Maybe you never defined them in general, but most of us learned someplace that the determinant of a 2x2 matrix is you take the A and the D, the first and the fourth thing here, multiply them together, the B and the C, multiply them together, and subtract the result. Okay? I presume everybody has seen that before. And if you haven't, okay, we're going to teach it to you. Now, 3x3 is a lot stranger, and without a description of why in the heck this is the way it is, it doesn't make much sense at all why it is. But once we spend a little time doing that, which we'll do later, then you'll say, oh, now I see what we're doing. Basically, what we're doing, I'm going to explain anyway, but just for 3x3. What you want to do with a determinant is figure out all the ways to write something from one row and one column times something from a different row and a different column times something from a different row and a different column. In other words, if I would take a number 1 that's up here, 1, 1. Now, the subscript here doesn't mean 11. It means first row, first column. Okay? And we usually don't put parentheses between the 1 and the 1, although we could. Okay? People didn't do that because in the old days you had to do typesetting and it was harder to do a comma. Now it's not so easy, not so hard. Anyway, if I take that number, now I have just destroyed or wasted or gotten rid of row 1 and column 1 in terms of picking something else in the second row that I haven't picked in the same column. Okay, when I'm in the second row, I'm in a different row. I got to be in a different column. So I got two choices here. I could pick 2, 2 or 2, 3. Sorry if it's not focusing right. If I pick 2, 2, fine. Now I've picked A11 and I picked A22. Then I got to pick a third one, but I can't pick something in the second row or first row or second column or first column. So now I must pick this one. So if I pick 1, 1 and 2, 2, I must pick 3, 3, and I multiply them together, and that turns out to be one thing in my determinant. Determinant is going to be a sum of all the different ways I can do this. If I had picked A11 and A23, then I'd be forced to pick A31. Now, if you go down here and look how we define it, this is what the book says, and I'm going to read now. The book says we can, a determinant of order 3 by 3 can be defined in terms of. Now, the author is wrong. We do not define the determinant this way. What we do is define the determinant and then see that we can determine it this. We can determine the determinant this way. So what the book more correctly should have said is a determinant of order 3 can be figured out, can be calculated by the formula he gives you. And the formula he gives you on page 655 or 855, whatever it is this formula. And this is the way some people learn it. And that is called expanding the matrix by the first row. And the reason is we have a number A11 there, we have a number A12 there, and we have a number A13 there. And those are the components of the first row over here. Now, if I take A11, like right here, then this over here is the row and column elements that I do not take from row or column 1. In other words, what's left over if I wipe out the row and column of, if I pick A11 and I wipe it out, what I'm left with is this little 2 by 2 matrix, and that's what you put here in the definition that he calls it definition. Once I pick A12, then what's left over if I wipe out the first row and second column, and what you should see on both sides of my thing here is A21, A23, A31, A33. That's what this one looks like. So what you got to do here to understand this determinant thing is figure out what in the world he's saying. But if you look at this again, what this is the two things I could have picked here when I was choosing stuff we talked about earlier. This is A11, and if I pick these two in the determinant, that's 2, 2, and 3, 3. If I picked 2, 3, and 3, 2, that would be these two. So the two different things I can combine with 1, 1 are in this determinant right here. And the point is that one of them is A11, 2, 2, 3, 3. The other is the other, and one of them is plus and one of them is minus. And this has to do with a mathematical subject called permutations, which has to do with changing the order of stuff. So 1, 2, 3, 3, 2, 1, those are called permutations of each other. So if we want to take the time, we could define a determinant in general as adding up a bunch of permutations of the coefficients, and half of them turn out to be plus and half of them turn out to be minus, because there are what in life are called, in mathematical life, are called even and odd permutations. Now, I'm not worried about that right now, but you need to, in section 4, you need to learn what a determinant of a 3 by 3 matrix is. And I'm putting up here a little something because I want to show you, and I want to emphasize the fact that this is all messed up down here. So what in the world do I mean by that? Well, I have found that when people learn about this stuff, when they take tests about it and stuff like some of you did last semester, we have something in section 4 called a cross product. And the way some people try to deal with it, not the definition, but once you learn what a 3 by 3 determinant is, you can use the structure of a 3 by 3 determinant to write down what the cross product is. Or you can learn what I am writing here as a 3 vector, 3 components. So one way to learn about cross product of A1, A2, A3 with B1, B2, B3 is to learn the following. It's A2, B3 minus A3, B2, comma, A3, B1 minus A1, B3, comma, A1, B2 minus A2, B1. This is a vector in 3-dimensional space, and you can learn the cross product by just learning this particular set of 3 things. Or you can remember about determinants and write it as a determinant. Now, when you mistakenly, but we do it anyway, write I, J, and K up here, these are not numbers anymore. So we are messing up the meaning of the determinant. But if I try to write down what it tells me, and I expand by the first row, I would be putting I times the determinant right here, and that is written here, I afterwards. I'd have this. This is the same right here. I'm sorry about my hands and stuff. This is the same right here as the thing earlier when we defined it, except it's multiplied by I instead of A11. Now, if I use I here, then I first put, I'm doing this on purpose, I put a comma, because some of you think you have a vector and you write it as commas. But if you use I, there are no more commas, because when you use I, you're replacing the commas with I, J, and K added up. So what we should have here is a plus, and unfortunately, because of the way determinants are, it turns out to be a minus. Now, that's because these two are turned around. So I'm running out of time here, it's 20 after. But what I tried to do here is to emphasize the fact that when you use I, J, and K, you do not use commas. Okay, you don't have this thing I, comma, J. If you either write the 3 determinants without I, J, and K with commas in between them, or use I, J, and K without commas, okay? All right, well, I think what I'm gonna do at this moment is stop this picture and stop the recording.